All right, so today we'll talk about AC circuits. What does this mean? I'm sorry? Yes, so to a circuit, you're, um, you're powering the circuit by an alternating current source. Okay? So, so here's an AC source and here's a circuit. Okay? Now, what we'll be interested in is, so this AC source, so here's the voltage that this source provides. There's the amplitude of the voltage. Omega is the angular frequency of the source. And so this voltage is a function of time. Okay? And what we are interested in is, we're interested in two things. So we'll connect this source to this circuit. And what we are interested in is what is the amplitude of the current being drawn. Okay? So to set that up, let me go back to a basic circuit. Okay. So here's the voltage, here's the current. Okay. What is the current in the circuit?
Voltage divided by resistance.
The voltage divided by resistance. Okay. So just like that, the amplitude of the current will be the amplitude of the voltage divided by the resistance of the circuit. So what we want to know is what is the resistance of the circuit. Okay. And the generalized term for that is the impedance, denoted by Z. Okay. So the amplitude will be the amplitude of the voltage divided by the impedance of the circuit. All right, so that's the first thing we want to know, what is the impedance of the circuit. The second thing we want to know is phi. Okay, so let's see what this thing is saying. Okay. Now, going back to the simple circuit. All right, whenever we learn about new things, we're learning in terms of the older, simpler things that we've learned. Okay, in this circuit, you've done this in lab, so let's say this was a variable voltage. I crank up the voltage. As I'm cranking up the voltage, what happens to the current? It increases. And when does it increase? Does it respond immediately? Yeah, so it responds immediately. Okay? And so this current increases immediately. Look at this fella, this equation. Okay, so here's you've seen a sine curve, it's like that. So the voltage is increasing, decreasing, and so on. But you see the current is lagging behind. It's not responding immediately. Okay? So we will need to find this. This is called the phase factor. Okay? Yeah, so in AC circuits, the current doesn't respond immediately to voltage changes. Okay? Now there's a very important thing that this thing tells you. Okay, so when you build a circuit, the circuit has some job to do. When will this guy do something? What do you need to do something?
A voltage potential across the circuit.
You need energy to do something. If you want to cook pizza, you want energy. Okay? All right, this guy tells you the rate at which this source is transferring energy to them. This is called a power factor. Okay? So you'll learn in this chapter, so this thing is a quantity that's between pi by 2 and minus pi by 2. If it's pi by 2 and minus pi by 2, or minus pi by 2, this circuit is not cooking anything. What happens is if this is pi by 2 or minus pi by 2. All that is happening is energy is transferred in one cycle, and it's transferred right back in the other cycle. Okay? So for this guy to cook with maximum power, phi needs to be, take a guess? 0. All right. All right. So those are the two things we're interested in. Okay? So what we're going to do is we're going to connect an AC source to a circuit. We would be interested in what is the Z of the circuit. What does the Z tell you? What is the Z? Impedance. And that'll give you the amplitude of the current being drawn by the circuit. And we want to know the power factor of the circuit. We want to know if the circuit is cooking or anything or not. Okay. So, all right. So those are the things we want to know. Do you guys understand where we are headed? So AC circuits is what we're dealing with. These are the topics we'll cover. All right. So AC generator. So first let's look at how to get an AC voltage. Okay. So here's an AC generator. It has a permanent magnet, and you have a wire ring. And if you rotate this wire ring, the voltage you get out here is a sinusoidal voltage like that. Okay. And you guys know how to rotate this thing. How do you rotate it? In a dam, the flowing water rotates it. In a windmill, the wind turning the blades rotates it, and so on. Okay. So this is the AC voltage you get. Now, if this thing is rotating 60 times a second, you get a frequency of 60 hertz. Okay. Angular frequency of the EMF is equal to the angular speed of the loop. Okay. So now this is the source we're going to feed our circuit. Okay. By the way, devices such as light bulb and toasters work equally well with AC and DC currents. Okay. It's easier with our model that we adopted 100, 200 years ago. We had large central power stations, and then power had to come to your home. And for transmission, AC is better. Okay. So motors are more easily adapted to AC currents. And who does most of the work in the world? Electric motors. 90% of the work is done by electric motors. Yeah. All right, so here is the electrical symbol for an AC source, and here is the source. The amplitude is that, okay? And what you get out of the socket, wall socket is, what do you get? The frequency is omega is 2 pi f, and f is 60 hertz is what you get out of the socket. And what is the amplitude?
240 volts.
It's the amplitude is about 170 volts. The 120 volts is the VRMS volts, which is max divided by root 2. Okay, so the 240 volts you're talking about is you get two live wires you use, which are 180 degrees out of phase. Okay, so that's how you get 240 volts. And you need that for your washing machines and all. All right, so we just said a whole bunch of stuff. Now the rubber will hit the pavement. Okay, so we're going to hook this AC source to our circuit. And of course, we want this circuit to cook. And it'll cook only when you supply energy to it. Okay? And the rate at which you supply energy is the rate at which it'll cook. Okay? Eventually, you will be interested in each of these devices, currents in each of these devices, just like we did DC circuits. You'll be solving circuits which you'll be calculating currents through each of the arms. We're not going to do that today. Okay. All right, so here's the voltage supplied to the circuit, and we want to know two things about this current. We want to know this phase factor, and we want to know the impedance of the circuit. Yep. All right, so what is the deal when you are learning about a new stuff? What is it that you do?
Find out stuff.
You start with the simplest stuff. Okay. So here's an AC source. Okay. And the simplest device we're going to connect is just a resistor. Okay. Are you going to live? All right, so there's the device we'll connect. Yeah, nowadays they don't even keep napkins around. All right, so there's the voltage. The current for a resistor, the current in the resistor responds immediately. Okay, so for the resistor, the current is simply written as is just V max over R sine omega t. Okay. So you're always comparing this to this equation. Okay. So keep this in mind. E max sine omega t, and IT is E max over Z sine omega t minus phi. Okay, so we'll compare this to that. So Z is R, which makes sense. The impedance of the circuit is just the resistance in the circuit. And what is phi?
The power factor.
And what is it? 0. Okay. So this fella cooks with maximum efficiency. Okay. So if you want to cook something, you want a purely resistive circuit. Okay. Now you will add inductors and capacitors and so on, and so you learn they'll have some purposes. Okay. And you'll see what you need to do to make the power factor 0 for that circuit, for a complicated circuit. Okay. All right, so for this first simple circuit, we found those two things. Z is just equal to R, and phi is equal to 0. And you see from this equation, you can see that as the voltage is changing, the current is in lockstep with the voltage. Okay. Okay, the power supplied to your circuit or your load, what is your circuit this time? It's just this resistor. Okay? The power supplied to your load is the instantaneous current times the impedance of the load. Instantaneous current squared times the resistance of your load. So there's your current. Okay, the current is sinusoidal, so it's the instantaneous power is sine square, is a function of is a sine square function. Okay, and here is the plot. So here's a plot of I square, and power is just I square times R, so just a factor of R. Okay, so you see here is the graph for the instantaneous power supply. Okay, there's one cycle. What is the frequency that you're getting out of the wall?
60 hertz.
60 hertz, so you're getting 60 cycles. So you see the power is peaking 120 times a second. So when you turn on that table lamp in your house, that thing is flickering 120 times a second, going on and off 120 times a second. Do you see it flicker? Why not?
Human eye can only register so many frames a second.
Yeah, 30 frames a second, so more than 30 times a second, and it'll appear continuous. Okay. Now, so there's the instantaneous value. Of course, we can't follow that. Okay. Now, if you had a strobe light, you could measure that. So that oftentimes we're just interested in the average power delivered, which is you just take the average of that, time average of that, and here's how you. So here's if for a periodic function of period t, here's how you take the time average. Okay. So if you did that to the sine square function, what you get is I max square r divided by 2. For a DC circuit, the power was I square R. Okay. So the power delivered here to this circuit was I square R. Okay. Now that's an expression we studied and we learned for a long time, and we remember that. Now this new power, the expression for this power is in the AC circuit is that this factor of 2 is annoying. You have to remember a new thing, new formula. All right, we don't want to do that. So what we'll do is we'll just define something new. RMS, which is just I max over root 2. Okay. And so this power becomes IRMS square times R. And this is exactly like the old expression. And we like that. Okay. So it turns out that in general, this is always true. Okay. So wherever you have a expression for DC circuits, you replace terms by RMS values, and you get the expression for the corresponding AC circuit. So for instance, let's do the following. So power for a DC circuit, power is given in as one of three expressions: VI, I square R for this circuit, and V square over R. Okay, so if you hook a resistor to an AC circuit, the power can be given in terms of can be written as VRMS times IRMS, IRMS square times R, or VRMS squared divided by. Okay, so whatever DC expression you have for a DC circuit, you just replace those values by RMS values, and you get the corresponding value for the AC circuit. Okay. All right, what does that RMS mean? Root mean square. Okay, and you'll get that if it's root mean square. Okay, so you square that and take the mean value of that, and square root of that will give you this I max over root 2. Okay. All right, so let's say we want to analyze a circuit like this. What is it that we do? We've gotten into the habit of?
Kirchhoff's voltage law?
Yeah, Kirchhoff's voltage law. We'll come up with a mathematical model, which will be a differential equation, and we solve the differential equation. That'll give us the current as a function of time. Oftentimes, that differential equation can be messy and so on. Again, now this is a simpler circuit. You could have a circuit like this, and there are other combinations, okay? And things can get messy, okay? So we are looking for easier ways of solving for the current, okay? And here is an easy way. So remember, we are interested in this expression. Okay? We're interested in finding phi, and I max is V max over Z. Okay, so Z will be something we'll be interested in finding. All right, so sometimes to avoid solving that differential equation, this is a technique that might be useful. Okay, let's go back to this. So let me remind you. Here's a vector A. Okay. What is the x component of the vector? Mm-hmm. Okay. So you see A is the magnitude of the vector and sine theta. Okay. So what does this voltage look like? You can think of that as the magnitude of a vector, and this is theta. What is happening to theta? As time increases, theta is increasing. Okay? As time increases, if this was the angle, this angle is increasing, so this vector is rotating. Okay. The current is also, there's the amplitude of the current and sine of theta. Okay, so that's the y component of the vector. Okay, so here's the technique. Okay, so here's a phasor is a vector whose length is proportional to the amplitude of the variable being represented, which is change in sinusoidally. So here's the current amplitude, here's the voltage amplitude, and there is omega t. And as t increases, this vector or phasor rotates counterclockwise at an angular speed of omega. So if you want the voltage across your load at 10 seconds, what do? So if you have a circuit like this, and here's your black box, and I want the current at t equal to 10 seconds. What do? Well, I have this phasor rotating at 10 seconds. If the phasor was there, the current vector was there, and the y component at 10 seconds is the value of the current. Okay? So it's as simple as that. So that's the idea. Okay? So now for a resistor, you saw that the voltage and current were in phase. Phi was 0. Okay? So they are in phase and they're rotating counterclockwise at angular speed omega, and the y component is the instantaneous values of the voltage and current across your load. Yeah. All right, you will see we'll use this technique for one circuit. Okay. Now you'll need this later on for more complicated circuits, but so you'll see the use of it in one instance. All right, so what have we done so far? We've connected an AC source. We've connected a resistor to this AC source. Z was equal to R and phi was 0. Okay, those were the two things we wanted to find. Okay. Now we're going to do the next thing. Okay, so we're going to keep things simple, okay, and connect all the elements that we know to an AC source. Okay, so far we've learned about resistors, inductors, and capacitors. Okay. So now let's connect an inductor to an AC source. Okay. What are the two things we want to know? Z and phi. Okay. All right. So here's an AC source there. Okay. What does it do? for a system that is changing with time, we build a mathematical model. And, if it's a differential equation, we try and solve the differential equation. Okay, so here's a closed loop. The sum of the voltages around all elements in the closed loop should add up to 0. So you go from here to there. There's that voltage across the source. And this guy, remember, he doesn't like changes in current. And if the current is increasing in this direction, he'll produce a voltage in the opposite direction. So there is the voltage he produces. And there is the differential equation. Okay. This guy is easy to solve. Okay, so I works out to that.
I'm sorry, I didn't quite catch that. Could you please say that again?
Thank you for your help. Okay, so we'll compare this to IT equal to E max over Z sine omega t minus phi. Okay, what is Z? Omega L. What is phi? Pi over 2. All right, so let's write that down. So the next element that we connected was an inductor. Z was omega L. Phi was pi over 2. All right. Okay, so let's notice something about Z here. Okay, Z here, see, for a resistor, it doesn't depend on the frequency. For an inductor, it depends on the frequency. Higher the frequency, higher the impedance. Okay, can you think of a reason why that might be? Very good. Okay, and an inductor doesn't like changes in current. Okay, so the more often the current changes, the harder it fights. Okay, so its impedance is increasing with, okay, and so its impedance will go to infinity. Higher frequencies will have a harder time driving currents. Okay, we told you phi equal to pi by 2. Does this guy cook anything? No. To cook something, phi needs to be 0. I mean, to cook at maximum efficiency, phi needs to be 0. Okay, so what's happening is this guy is storing energy there, which is given right back in the next cycle. How does an inductor store energy?
As a magnetic field.
In magnetic fields. Okay. Now, okay, so we're doing all this for simple things and stuff like that. You might be wondering why we're doing this. Okay. Now this could be a city. See, this is the AC power coming. If you want maximum power delivered to the city, what do you want to do? You want to make sure that the phase factor is 0. The power lines that are bringing in power have inductive impedance to them. Okay? So you have to make sure somehow you want to bring phi to 0. Okay? So we'll look at that. All right? So what is the next element that you're familiar with? Capacitors. Okay. By the way, so let's look at this. I want to show you one more thing about this. So you can see that there's the voltage, and the current is lagging behind the voltage by 90 degrees. So here's the diagram. So by the way, the impedance is given a special notation. So the impedance for an inductor is denoted by XL, the subscript L telling you that it's the impedance of an inductor, and it's equal to omega L. And you can see that this guy behaves differently than a resistor. See, here is the current, and the current, there's the voltage, and the current is not in lockstep with the voltage. It's 90 degree out of phase. See, in this part, the voltage is decreasing and the current is increasing. Okay? And so on. And here, the so anyway, they're not in lockstep. Okay. So there is the voltage phasor, and there is the current phasor. Okay. And all you do is rotate it at angular speed omega, and you want the instantaneous value of the voltage across the inductor. You take the y component of that. Instantaneous value of the current is the y component of that phasor. All right, so now let's connect the third element that we know. Yep. All right, so the voltage, there's the voltage. And so for a capacitor, capacitance is defined as QT over V. So VT, so Q, so QT is VT times C. Okay, so VT times C, and there's the voltage that the capacitor sees. Okay, and the charges move instantaneously. They don't move instantaneously, but at the speed of light, and that's none of our circuits could. Okay, so as far as we are concerned, it's moving instantaneously. Okay, so there is the current, and there's the charge on the capacitor, and the current is in the circuit is just dq by dt, which is that. All right, so I is V max 1 over omega c sine omega t plus pi by 2. Okay, so what is our z value? 1 over omega c. Okay, so you see the z, as frequency increases, z is decreasing. And does this make sense? So what we are saying is, as for high frequencies, it's like the capacitor is not even there. Okay. What's that?
That kind of makes sense.
Yeah, so it's charging so fast that it's not even there. Okay? For high frequencies, it's not even there. What is phi? Negative pi over 2. This fellow is not cooking either. What is going on?
It's discharging whatever it gets charged by.
It's charging, storing energy in electric fields, and then the next cycle, that energy is given right back. Okay. If you're cooking, you gotta consume energy. If you want to do anything, you have to use energy. If you're not using energy, then you're not doing anything. All right, so now we have our 3 basic elements. So we have our 3 basic bricks, and now we can build more complicated things. Okay? So Z, and this has got a special name. So we'll add the special name here as well. Z is called XL, which is omega L. Z is called XC, which is 1 over omega C. All right, so now we'll build, we have the 3 basic bricks, and we'll build more and more complicated things. So here, here's a parallel combination. I'm just showing you examples. And you can imagine all kinds of other stuff. Yep. and so on. This is the guy we'll study. All right. Why? Oh, there you go. All right. Okay.
Quick question. I think
Okay.
I might have slipped out earlier when you
Mm.
explained it. What exactly is the Z supposed to be for? Like, it's...
Z is the impedance of the circuit, the resistance of the circuit. Yeah. All right, so again, you can see that from this expression that the current is not in lockstep with the voltage. In fact, the current, so the way we had written the current, okay, why did we write the current like this? Okay. What causes a current in a circuit? Voltage. Here's the voltage, here's the cause, here's the effect. You would think that the effect would follow the cause. So that's why we wrote it as minus phi. Okay? This fellow is strange. This guy is leading the current by pi by 2. All right? All right, so that's why we had defined it like that. Okay, so XC is the impedance of the capacitor, which is 1 over omega C. And as you can see, XL and XC are frequency dependent. For high frequency, XC goes to 0. Okay, as frequency goes to infinity, XC goes to 0. Yep. Here's the voltage, and here's the current, which is 90 degrees out of phase. So the phasor for the capacitor is 90 degrees ahead of the voltage phasor, and these things are rotating at angular speed omega, and the instantaneous value is just the y components. Yep. All right, so now we have our three pieces. So we're going to consider one particular combination. There are many, many combinations possible, but we'll consider the hardest combination. So, all right, we'll consider series combination of these three elements. Here's our AC source. Okay, we'll connect to, this is a RLC series circuit. Okay. And we will be interested in two things for this circuit. What is the Z of the circuit, and what is the phi of the circuit? Okay, so again, you could use Kirchhoff's rule, set up the sum of the voltages across this thing is 0, and try and solve that differential equation. Okay, so I'll write it down for you guys. V max sine omega t. I'm writing Kirchhoff's rule, starting here, going there. Then minus I t r minus L di by dt. And then V is minus QT C equal to 0. Okay. I is di by dq by dt, and so this would be a second order differential equation. Okay? And this will be messy, so we don't want to solve this. Okay? So we are going to use the phasor diagram, which is an easier way to solve this. Okay? So let's say there is the current phasor for that circuit, and the voltage across the resistor is in phase with the current. So there is the voltage phasor across the current, across the resistor. Okay. The voltage across the inductor is 90 degrees ahead. So the voltage phasor across the inductor is that. And there is the the voltage across the capacitor is 90 degrees behind. Okay, so these phasors are the voltage across each element. Okay, and what is the voltage across all the elements? It's just the sum of those vectors. The sum of this vector plus this vector plus this vector, which is that. So that's the total voltage phasor across the circuit. There is the total voltage phasor across the current. And now all you do is just rotate it counterclockwise at omega t, at angular speed omega. And the y value will give you the instantaneous voltage and current. Okay, so there's the total voltage, and there's that angle phi. Angle phi is the angle between the voltage phasor and the current phasor of the circuit. Okay. So V max, this guy is, there's the x component of that vector, and the y component of the vector is this minus that. So V max is VR square plus VL square, VL minus VC square. VR, the amplitude of the voltage across the resistor, is the amplitude of the current times R. Amplitude of the current times XL minus amplitude of the current times XC. The current comes out times that. For a DC circuit, what is the voltage is I times R. Okay, the voltage across a resistor is I times R. So here we go. So we have exactly the same expression. V max equals I max. So this must be Z. Okay, so that is the impedance of that circuit, RLC circuit, RLC series circuit. So that's the first thing we found out about it. Notice something, okay. The impedance of the circuit, these guys are frequency dependent. So the impedance of the circuit depends on the frequency. Okay, you could potentially find a frequency where this would be 0, and that would give you the minimum impedance and maximum current. Okay, and you'll learn in a second, when this guy is 0, that's when phi is 0. That's when maximum power is delivered to the circuit. Okay. All right, so we found the first thing. Now we want to find phi. Okay. So you can see from this diagram, this is proportional to XL minus XC, VL minus VC, so it's XL minus XC, and this is proportional to VR, which is proportional to R. Okay. So tan phi is this over that. So phi is tan inverse of XL minus XC divided by R. Okay. So you can see that when this is 0, phi is 0, of course. Okay. When XL minus XC is 0, phi is 0. Okay. So there are the two expressions that we wanted. We found the two things for a series RLC circuit using the phasor diagram without solving this differential equation. Okay. All right, now let's, we've been telling you that this is a power factor, so let's look at it. Okay. So by the way, so here are various elements of, here's the table. For just the resistors, there's the impedance and the phase angle. Remember, these are the two things we want of any circuit. For this guy, XC and minus 90 degrees, plus 90 degrees. For this guy, for a combination of resistor and capacitor, okay, so the phase angle will be between minus pi by 2 and 0. For this guy, it'll be between 0 and pi by 2. For this guy, if XC is greater than XL, it'll be negative, and if XL is greater than XC, it'll be positive. Okay. So again, see, what we are interested in for any circuit is the impedance and the phase angle. And this table lists for various circuits. All right, now let's look at the power factor. Okay, so here's our circuit. And I'll draw the circuit as a black box. Okay. So the instantaneous power delivered to this thing is I, the current, times the voltage. Okay. There is the current delivered to the circuit, and there's the voltage. All right, of course, this thing is changing quite fast, and so we're not interested in the instantaneous values. We're happy with the average power. So you just take the average of this function, okay? And how do you take the average of that function? That's a function of time. You just do the following integral. So it's a function of time of period 2t dt 1 over t. Okay, that's how you do the average. So you can do that for this function, and here's what you get. Okay. And again, for a DC circuit, one of the expressions for power was V times I. So we are annoyed by this factor of 2. And remember, how did we fix that? We just called RMS values, defined RMS values. So average power is VRMS times IRMS, exactly like that, except for there is this factor, cosine phi. So you see the average power delivered is VRMS times RMS times cosine phi. Is phi is pi by 2. When this guy was an inductor or a capacitor, it was plus or minus pi by 2. This was 0. No power was being delivered to that circuit. This could be a city, and if phi is pi by or minus pi by 2 or pi by 2, it'll be in the dark. This has the maximum value for phi equal to 0. Yep. For phi equal to 0. That's when maximum power is delivered. Okay, to that black box, city, circuit, or whatever. Okay. So that's the power factor. So the power factor is 0 for purely capacitive or inductive circuits. In such circuits, no power is dissipated. All right, so in a DC circuit, I is V over R. Okay. So this can be generalized. I max or IRMS is VRMS divided by R gets replaced by Z for the circuit. All right, now, so there's the amplitude of the current, well, RMS value of the current, okay. This is frequency dependent because these guys are frequency dependent. Okay, so all you have to do is, now, if this goes to 0 at a particular frequency, when this goes to 0, then this guy is maximum, okay? And that's what this is showing you, okay? So omega naught is the frequency at which this is 0. So XL minus XL is 0 for omega equal to 1 over root of LC. Okay. Remember, omega L minus 1 over omega C equal to 0. And you solve this, and you get, that's the value for which it's 0. Okay. So at that particular frequency, this is 0, and the current amplitude is the maximum. Okay. So, and at that frequency, maximum power is delivered to the city. Okay. What is the frequency you are getting from the wall?
60 hertz.
Okay, 60 hertz. Okay, so at that frequency, you want XL minus XC to be 0, if this is your city. If this is your circuit, at that frequency, you want XL minus XC to be 0. Yeah. All right, so you can see that, so this is just plotting amplitude of the current and omega minus omega naught. Omega naught is the natural frequency of that circuit. Okay. And at that frequency, there is the maximum amplitude of the current. All right, so here's Hoover Dam, and here's your city. These transmission lines have XL, an inductive impedance. Okay. You want maximum power to be delivered to your Imax, Vmax. So these transmission lines have XL to them. Okay. So what is it that you want to do? Well, you want to add XC just before you get to the city, such that at that frequency at 60 hertz, this is 0. And then maximum power is delivered to your city. Okay. And that's what these guys are doing. You see these outside all towns and stuff like that. Right, so power capacitors are used to balance the impedance of the effective inductance of transmission lines. Okay. So that's to make the phase factor 0. Okay. You guys have seen this in your town? Yep. All right. We'll see in a second. So you see, this is the current, okay? And so here's the power being delivered to that circuit. Power is V square R, and so as a function of the frequency, this is the natural frequency of the circuit, and it goes like this. Okay? Power is also equal to I square Z. Okay, so when you plot that, it goes like that. The narrower this curve is, the better the quality of the circuit, frequency response of the circuit. Okay, why? So you could use that circuit to identify this frequency. Okay, so these guys are not disturbing you. Okay, so this kind of stuff is important in tuning circuits. Like the current, the average power transferred from the AC generator to the RLC circuit peaks at a resonant frequency. So at resonant frequency, what is the resonant frequency again?
The highest
Uh,
current, I believe, at the
yeah, XL minus XC is 0, and current is max. Current amplitude is maximum. Okay. Sharpness of a resonance is given by the quality factor. The quality factor is the frequency divided by the width of this curve. And the width is at half maximum. See, there's the maximum and there's half maximum. Okay? So there's width at half maximum. All right, so here's your circuit. This is your power source. What is that? I'm sorry?
It's a radio wave.
That's right. It's an electromagnetic wave, and this is your radio wave. Okay, so you're catching this wave using this dipole antenna. Okay, and so if you have multiple waves, and this is the frequency you want to catch, what is it that you want to do? At this frequency, you want to make XL minus XC equal to 0 for this circuit. For this frequency, if XL minus XC is not 0, it's only delivering this much power. at that frequency, if XL minus XC is 0, it's delivering this part. The other frequencies are delivering this part. So signal to noise ratio will be high. Okay. And narrower this thing is, okay, then what is the advantage of having narrower, higher quality factor?
You get a clearer sound, you have less noise.
You can have more signals.
Very good. Okay. You can have a station here, you can have a station here, you can have a station. Okay. And so narrower that thing is, better the quality of your tuning circuit. Okay, so on your FM radio, what are the frequencies you can catch?
80 to 109.
Okay, so 89.9, 90.1 megahertz. .1 megahertz. Okay, so the difference is, the distance is 0.2 megahertz. That's this distance. Okay, so you want a signal here, and then the next one is, next closest frequency you allow is that. You guys, I know they're not very popular, but there's these tuners that can catch frequencies 89.9 and 90.0 and so on. So there are not enough stations that broadcast that, but so their quality factor is twice as good. Yeah. All right, so a radio is tuned by varying the capacitors to match the frequency of the circuit with that of the incoming circuit. So when you're tuning the circuit, what is it that you're doing? You're making this 0. Okay. We talked about transformers. You supply an AC source. The changing magnetic field is coupled to this secondary coil, and you can see the output voltage there. Okay, so if N2 is greater than N1, it's a step-up transformer, and if N2 is less than N1, you have a step-down transformer. You guys saw that in the current setup. So here's the power plant, and you have to step up the voltage. In the US, we transmitted at I believe 780,000 volts, or maybe 850. I think 780,000 volts. Yep. And then you have to step it down. Why do we step up? Why do we transmit power at high voltage?
More efficient.
Yeah, minimize losses. Minimize transmission losses. All right, now we'll talk about just a couple of circuits. Can you hold up your brick, my friend? Okay, so that's a rectifier. Okay. His laptop doesn't like what's coming out of the wall, so we got to rectify that voltage to what his laptop likes. Okay, so this is what's coming out of the wall. Here's a diode. A diode essentially is a one-way gate. It only allows current this way. Okay, and it doesn't allow current this way. So you connect a diode to a AC source and watch the voltage across here. If you connect a voltmeter here, this is what you see. You see only the voltage during the cycle where the current is passing this way. Okay, when the current tries to pass this way, this guy stops it, and so you're not seeing that voltage. All right, so you've solved half the problem, but you've also thrown away half your money. Okay, you don't want that. So here's what we're going to do. We're going to go buy 4 diodes. Okay, and now if you hook it up like this, okay, so during the positive cycle, Okay, so during the positive cycle, current will flow like that. During the negative cycle, when this is negative, wait a second. Okay, during the negative cycle, it'll flow like this. So now you have current flowing through both cycles. So you feed this voltage, and what you see across here, if you connect a voltmeter here, this is what you see. So what did you do? Well, you didn't throw away 50% of the money. Okay, so you got it, all the money on the table now. But that guy, the laptop, doesn't like this. You got to smooth out this guy. And so what you do is, if you put a capacitor here, you put a capacitor there, and now if you measure the voltage across this guy, you get a smooth curve like that. Now this is a simplification, but those are the main elements. So that's what's in the brick. Okay. Here's a capacitor. What is the impedance of a capacitor? 1 over omega C. For high frequencies, it's a short. The impedance is 0. So for high frequency, it's a short. The current will just go through it like that. Okay. For low frequencies, for 0 frequency, its impedance is infinite. So you see a large impedance, and you can measure a voltage across there. So if you're measuring voltage across the capacitor, you can see the low frequencies, and the high frequencies are let through. So this is a low-pass filter. Why is this thing useful?
Can improve fidelity of the signal.
Okay, so when you dig up and lay a line, that's the most expensive thing to do. Now that you have a line, you want to put various signals. You put a low frequency signal as a carrier signal, a high frequency signal as a carrier signal, and stuff like that. Now you want to be able to separate those guys. Yes, so in a given physical line, you can now pack more information if you can separate the frequencies. Okay, so it turns, this is old time stuff. I don't know, most of you probably have never seen something like this. He even admits it. This is not that old. Anyway, what's that?
DSL.
Yeah, so what this was phone companies provided internet service over the telephone lines. Telephone conversations were sent on low frequency carrier signals, and internet information was riding on high frequency. So this was, voice was riding on this thing, and internet data was riding on this thing. So you had to separate these two signals. This device let the low frequency signal, carrier signal pass through, and then you can tease out voice from that. Okay? So the advantage of these filters, these pass filters, is on a given line you can have multiple signals. This is a high pass filter. Okay, so at high frequencies, this is essentially acting as a short. For low frequencies, it blocks the signal. For high frequencies, it's acting as a short, and you can see those high frequencies if you connect the voltmeter across this guy. Okay. All right, guys.